Okay, so here we go for the exam 1 review. So these are going to be the free answer portions of the exam. So this is one example of the types of questions you'll see. So there'll still be some multiple choice questions on there. Those are going to be on the sort of general concepts and trends for that. But for the free answer part, these are the types of questions you'll see. So if you can do these, you're doing okay for that. So one of the questions will be about dipole moments. Okay, so this has to do with the electronegativity. So I will give you the values of the electronegativity, and you need to know the trend. That the closer the element is to fluorine on the periodic table, the more electronegative it is. But I will give you the numbers. You do not have to memorize the actual numbers, stuff like that. And so what you're going to want to do is you want to look at every polar covalent bond in here and indicate that. Within the molecule, indicate which which is the positive side, which is the negative side. Now you can do that with arrows. You could also do it with the little delta symbols, right? So the arrows is like that. So you can do it with the symbols, the delta plus, the delta minus, or you can do it with the arrow. Okay, so with that. So remember, the crosshatch goes on the positive side. The arrow goes on the negative side. Okay, so between here you've got a carbon-carbon bond, so that's going to be that's just going to be completely covalent with that. But between this carbon and the oxygen, now the fact that that this is a double bond does not matter. You're just looking at the two atoms themselves. Okay, so with that, so on the periodic table, right? So with that, so oxygen is closer to fluorine than carbon is. So with that, so that means that the oxygen is more electronegative. So here the arrow is going to go that way. Okay, it's going to go, this is going to be on the towards the less electronegative side. The arrow goes towards the more electronegative side. The same thing happens with this one. It doesn't matter about the charge, the formal charge on this. You're just looking at the two individual atoms. Okay, so here we go. So again, this one's going to go like that. Okay, so for you want to look at each individual polar bond on the molecule. Okay, now you also want to draw the arrow for the appropriate overall dipole moment. Okay, so basically what it is just going to be halfway in between those two. Okay, so if it's like this, it's going to go like that. If it was over here, it'd go like that. Right. So if the arrows were like this, right, the arrow is going to point out like that. Okay, so with that, so if it was down like this, the arrow would point down like that. Okay, so with that, so now if they were across, right, so they were equal and opposite. Okay, they would cancel each other out, and so there'd be no dipole. There'd still be dipoles on the individual bonds, or there'd be, you still have to do show the electronegativity on these things, but since they cancel out, you just indicate no dipole. Okay, so halfway in between here, right, is an arrow that goes like that, right? So and then you just mark this as overall. Okay, so it's halfway in between these two. Okay, there you go. Okay, so for this one, you're going to want to take a look at this structure, and all the atoms are shown. Okay, you do not need to add atoms. All you need to show or add extra bonds and lone pairs where appropriate to finish up the molecule. Okay, to finish out the Lewis structure. Okay, so you have to remember, right? So if you think about this, right? So if you're thinking about carbon, if you go across periodic table, carbon, nitrogen, oxygen, fluorine, right? So you think about those columns. Okay, and actually even neon here. Okay, if you want to think about bonds versus lone pair sets. Okay, you think of it here. Carbon likes to have 4 bonds, no lone pair sets. Nitrogen likes 3 and 1, 2 and 2. Fluorine has 3 and 0, and neon has 4. I'm sorry, going the wrong way. 4, 3, 2, 1, 0, and this is 3 and 4. Right? Sorry about that. I got a little ahead of myself. So 4, 3, 2, 1, 0. Right? How many bonds at once? And to complete the octets, it's 0, 1, 2, 3, 4 bond. Sets of lone pairs. Okay, so you can sort of think about this as you go across. Okay, so we have to think about this when we're trying to fill this out. Okay, so this carbon here, right? It has its 4 bonds. It's happy. This carbon here, right? It has its 4 bonds. It's happy. So this carbon here, it only has 3 bonds. Single bond here, here, and here. Okay? So you can't make, so hydrogen only wants one bond, so you can't put a double bond there, right? So to get its fourth bond, you can't put it here, because if you put it here, right, you would end up giving this carbon a fifth bond, which you can't do. Okay, so now you need to look at this one. Can this one take it? Well, this one only has 3 bonds as well, right? Here, here, and here. So that means you're going to turn this into a double bond. So now it has its 4 bonds, and this carbon has its 4 bonds. So it's happy. Okay. Now this carbon here, right? So it only has 3 bonds as well. Okay. So again, we can't make it here, right? Because this carbon, we figured out we've made its 4 bonds. Okay, this carbon here, it has its 4 bonds, 1, 2, 3, 4. Okay, so it's left with is this oxygen. Well, this oxygen only has 1 bond right now, right? Typically, oxygens like to have 2 bonds, right? So we could make this into a double bond. Okay, so now this carbon has its 4 bonds. Okay, but the oxygen doesn't have its octet, right? So it only has 2, 4 on here, but it really likes to have 2 sets of lone pairs. So we can add lone pairs here to complete out the Lewis structure. Okay, so now this carbon here, it has its 4 bonds, so it's happy. The hydrogens are fine, but this chlorine, okay, it's in the same row as the fluorine here. It has its 1 bond, but it likes to have 3 lone pairs. So you're gonna have to don't forget about the the chlorine in here. It wants its lone pairs, and so now we're done. Okay, so you need to go in here and remember this. Think about this chart and figure this out. And try to add the lone pairs and any sort of extra bonds, double and triple bonds, as needed to complete the octets for these atoms. Next up is formal charge, right? So what's going to happen is I'm going to give you a molecule, right, and I have a big arrow pointing right there. I want that. What's the formal charge on that atom? Okay, so like that. So if you remember, right, so with that, so each atom. Right, each bond has 2 electrons here, right? Bond, 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 right? So with that, so we're interested in that oxygen, so we're going to slice that each one of those bonds in half, and the electrons get split evenly. Okay, so now that oxygen is going to look like this. These individual electrons from the single bonds here, plus a set of lone pairs. Okay, so what you do is you say, okay, how many valence electrons does oxygen normally have? And you just have to count over 1, 2, 3, 4, 5, 6. Okay, so on the periodic table, it starts off with 6, and then you subtract what it has now, which is 1, 2, 3, 4, 5, and so the formal charge is +1. There you go. So I would write it next to the arrow, please, so I know which one you're talking about. Okay, so there you go. So it's always what it says on the periodic table minus how many electrons it has now. Okay, so for the condensed structure, okay, that's next. I'm gonna give you a Lewis structure. You're gonna have to go to condense. Okay, so here's the sort of main chain of this structure here. Okay, so you're probably gonna want to start with 1, 2, 3, 4, 5. Those 5, 2, 4, 5. Okay, so with that, so now for the one way that you can do it is then you notice you have the this carbon coming away. So you could either put in parentheses, we'll get to that in a second, or you can put it show a bond here going away, and that either one is fine. Now you assume that if you don't see a bond, it's a single bond. Okay, but we do have this double bond here, so we have to show it. So it's between this third and fourth one here, so we're going to have to show that double bond there. Okay, so now we're ready to fill things in. So these 3 carbons, those 3 hydrogens go in this carbon, so we're going to put it afterwards. Okay, this carbon here has that CH3, this CH3 here, plus that hydrogen. Okay, that carbon here has 1 hydrogen. This carbon here has a hydrogen. Okay, and this carbon here, now it has 2 hydrogens, but it also has this OH here. Now we don't put the H in with this H here. The reason is because we don't want to get that confused. If we were to write CH3O, it would look very similarly. You might get it confused with a methyl group, and it'd be most chemists would kind of look at you funny. stuff like that. And so what you do is you say, okay, we're going to have these two, and then just write explicitly out the OH here. The other way you could do is you could put that in parentheses if you want to see it. I certainly don't care, and most people don't, stuff like that. And so that's perfectly legal. And so if you want to put it separately in parentheses, that's totally fine. The other option would be to put this down here and put this in parentheses as well. So it'd be CH3, CH3. Okay, and the parentheses indicate, and again, we don't combine this H with these H's here because they are going to be considered independent of each other. Okay, CH, double bond, CH, CH2, OH. I'll take it either way. I could do it without these parentheses, that's fine. Either way is perfectly acceptable to me. But that's just which way you like doing it. Okay, so I'll take either answer. Okay, so convert the skeletal structure. Okay, now I like using the dots a lot, stuff like that. So and again, when you guys are learning these things, you'll see me do the sawtooth, and we'll talk about why that is later, stuff like that. But if you just do it as dots and connect the dots, I'm perfectly fine with that. Okay, but the first thing you're probably going to do, right, is to go in and now I am going to ask you to put right into lone pairs. Okay, so the so be sure to do that. Okay, but to come in here and just circle if there's a functional group. Okay, so here, you know, that has sort of non you know, to just be aware of so you don't forget it, right? So if there's like a fluorine hidden in there somewhere, you may want to circle it just so you don't forget it. Okay, so I usually try to circle these things. Okay, now you will have to don't. Okay, so with that, so we'll get to the hydrogen in a second. So just so you don't forget that. Okay, now the other thing you can do is then say we do not need to show hydrogens that are coming off of carbons. Okay, so basically you can just kind of scratch these things out. Okay. Now this hydrogen you have to show because it is hanging off an oxygen, so you have to show that. But these guys here, these you don't have to show. So usually what I'll do is I'll just transcribe where those carbons are as dots. Okay. Now there's a carbon-carbon bond here, so then you just connect the dots. Now between 2 and 3 here, there's a triple bond, so we've got to show that. Single bond. There we go. So single bond, single bond. Now for these, you have to show, okay, along with the lone pairs, okay, and then another bond, and then OH, okay. Now you could write it O-H or OH. I don't really care, okay, but that's perfectly acceptable, okay. That follows all the rules for that. Now if you were gonna draw it as a typical sawtooth, you would probably do it something like this. Oops, OH. Sorry, that's OH. Now, and do it like that. Okay, now there is an issue with the triple bond. In fact, this actually wants to be 180 degrees. We'll talk about that later. We'll talk about why this isn't quite correct later, but that's perfectly fine. I'll take either one. I don't care. Stuff like that. Again, you guys are learning this. You guys, as we get used to more and more, you guys will get used to doing this. But for right now, this is perfectly acceptable. So, okay. So next up, you're going to be given an atom, okay, and you need to get the electron configuration. So you have to show me the orbitals. You have to label the orbitals, stuff like that, and show me how the electrons are getting added and, you know, sort of stacked up. Okay. So what you're going to want to do is take the periodic table. I am going to give you a periodic table, okay, and we're going to go across. So phosphorus is here, okay, so you're going to start going across. Okay, so the first one here, so there's 15 electrons in the phosphorus, okay, stuff like that. And so you start off with 1s. Now 1s is a little weird because really helium should be over here, but its properties are over there, stuff like that. So it's a little odd. So you just start off with 1s, and then you can go beyond that. It makes more sense. Okay, so we start off with 1s. The next thing is we start off with 2. You know, we've already done a 1s, so now we start filling in the 2s. Okay, and that has one shape, so you get 2 electrons per shape. Okay, and now here, this is the p block. Okay, this is the s block, p block, d block, f block. Okay, it's the second orbital type you come to. Okay, so that actually starts off with 2. Okay, and it has 3 shapes to it. Okay, so this would be the third, as you would go across. This is the third. This is the D block here. This is the third block third orbital type you would come to. So that actually starts off with 3D. Okay, I always remember because like 3D movies and 3D pictures and things like that. That's where you start with. So that one right here would be this row here is the 3D 4D. This down here, if you were to keep going and get to come down here, this is this you start off with. It's the fourth orbital you come to. So this starts off with 4F. So this is the 4F and the 5F. Okay. So with that, we're not going to get that far down, but just be aware that the S's start with 1, the P's start with 2, the D's start with 3, the F's start with 4. Okay. So with that, but the P's have 3 different shapes, right? So this has 1 shape. This has 3 shapes. This has 5 shapes. This has 7 shapes, right? So it's an odd number of shapes stacking up. Okay, so with that, so this one we have enough to fill all these in. Okay, so with that, so we're here. Now we come back over to here. So we're back to the S block. So we've already done 1 and 2. So now we're back to the 3S. Okay, and then we're going across here. Okay, now we've already filled in the 2P. So now we're into the 3P. Okay, 1, 2, 3. Right. So now, okay, now we don't have enough. Okay, we're up to 12 at this point. Okay, so now we go. Right, so now we have 1, 2, 3 to fill in, and the way you want to do this is to fill them individually and then pair them up. Okay, so what I usually do is up, up, up. So if we were over here to sulfur, it would be up, 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 and then down. Okay, so fill them up individually, then pair them up. Okay, I usually do ups and then downs, but it doesn't really matter. Okay, so there you go. Okay, so for the resonance structures, okay, now I'm going to give you this as more of a proper Lewis structure, although I could give it to you like this technically, stuff like that. But one of the things you're going to want to do, especially when you're just starting out, is go ahead and fill in all of the hydrogens. Okay, fill in all the bonds so it's a little bit easier to see. Okay, so what you're going to want to do is you're going to want to take a look at the first thing you want to do is take a look at the molecule and see if there's what atoms are eligible and not eligible for the resonance structures. To be eligible, you have to satisfy just one of the criteria. You either need to have a lone pair, you need to either have a charge, or you need to be part of a double or triple bond. Okay, so this carbon here is eligible because it has a charge. These two carbons are part of a double bond, so are these two. Okay, but this carbon here is not. Okay, it only has single bonds. It doesn't have a lone pair. It doesn't have a charge. Okay, so it's not eligible to be part of it. It's just these 5 carbons here. Okay, now it doesn't have to just be carbons, right? So if there's an oxygen in there or nitrogen, if it has a set of lone pairs, it can come in and participate, stuff like that. But hydrogens aren't because they only need 1 bond. Okay, so after you figure that out, you're going to say, usually 9 times out of 10, you're going to start with that charge and say, what's wrong? Why does that particular atom have a charge? And what you're trying to do is you're trying to push electrons around to help out the atom that has the charge. Okay, so this atom here has 3 bonds, right? Carbon wants 4 bonds, right? Stuff like that. And so what it's going to do is it's going to look at its neighbor. It's going to look at this neighbor. Well, this neighbor is not eligible, so it can't do anything. But this one is. And so it asks this neighbor, hey, can you help me out? Can you give me the 4th bond? And so what it does is it says, sure, I'll move this bond up here. Okay, so now okay. So now there's a double bond there, right? That one didn't move, so that one's still there. Okay, but now this carbon here, now this carbon only has 3 bonds, so it has a charge. Okay, it helped out that carbon, right? Now it has its 4 bonds. Okay, but now this one only has 3. Okay, so it kind of screwed him over, right? So with that, but that's okay because he's going to talk to this neighbor and say, hey, can you help me out? And he says, sure, I'll move that bond, one of these bonds over there. Okay. Okay, so now that double bond's been moved over here. So now that guy, right, It only has 3 bonds, so now it has the positive charge. Okay, so now the problem with this one is it can't ask this neighbor. Okay, it can, but it's not eligible. Okay, so you're out of your eligible atoms to take advantage. So then you stop. Okay, so here's the 2 additional structures, because you keep going around until you either hit the end of the line or you hit your first ineligible atom, and then you're done. Okay. So there you go. Okay, so name the following compound. Okay, so so what you're going to do, right, is put in your dots. Okay, like that. Okay, so you come in here, right? So we say, okay, so you're either part of a straight chain or you're part of a ring. Okay, so for here the straight chain is just 1. Right here it's 5 around, right? So your main chain is going to be that ring here, so C5, right, which would normally be pentane. Okay, but to indicate that it's a ring, right, we're going to make this a cyclopentane. We're going to put that cyclo prefix in there to make sure that it that you understand, that indicate that it's a ring. Okay, so we've got our main chain, so now we've got our side chains, right? So we have a 1 carbon group, so we have a methyl. Okay, and we have the F here, which would be fluoro. Okay, now we need to figure out the numbering. Okay, so with that, so we're going to say, okay, so we're going to start with we're going to say, okay, well, wherever something is attached or around the ring, we're going to say that that's 1 and see what the numbering goes. So then you say, okay, clockwise versus counterclockwise. Well, the nearest side chain neighbor is clockwise around here, right? So it's 2, 3. So we'll just keep going around 4, 5 like that. So here the fluoro is 1 and the methyl is 3. Okay. The other option would be to make this methyl 1. Okay. Which again, the nearest side chain neighbor is right here, so the quickest way to get there is to just go counterclockwise around. So 2, 3, 4, 5 like that. So now it becomes 3 and 1. Okay, so you add them up, there's 4 and 4, and then there's a tie. Now there's no other way to break this tie. Okay, and so what we want to do is we say, okay, what we have to do is we say, okay, what we're going to do is we're going to say the first alphabetically is going to get the lowest number. So that means this number wins, right? So we had to break the tie somehow, and that's what they decided to do. Say the first alphabetically is going to get the lowest number, which would be 1 in this case. Okay, so so fluoro comes before methyl, so it's going to be 1 fluoro, 3 methyl, and then always put the main chain last, so cyclopentane. There you go. Okay, so name here, so we have an ether. Okay, so here we go. So drawing our dots for our carbons. Okay. Now, just as a reminder, they when you're coming in here, that bond is going into that oxygen. There's not a carbon there, nor is there a carbon there. Okay, there's a carbon here, and that's what we're showing is the bond is going into that. There's a carbon here, and you're going. They have a bond into that oxygen. There's a carbon here, and that bond's going into that oxygen. Okay, you have to be aware of the difference between this carbon here, or this bond here, that's ending in a point. Okay, as opposed to this one that's ending in an atom. Okay, if it's ending in an atom, that means that there's not a carbon there. Okay. Okay, so here we go. So we're look on both sides of this, right? So both sides of that oxygen, right? So here we have a 4-carbon piece, and here we have a 2-carbon piece. Okay, so that means this side here is going to be our main chain. Okay, so it's 1, 2, 3, 4. So C4, right? So that becomes butane. Okay, so that means this guy here is our side chain. It's 2-carbon piece connecting through an oxygen. So typically that would be, right, a 2-carbon piece is an ethyl, but because that is connecting through an oxygen, it becomes ethoxy. Okay. So now this is just our regular side chain, right? So now we need to do from one side or the other, right? So if we do 1, 2, 3, 4, right? So that would be 2. The other option would be to start here, be 1, 2, 3, 4, right? It would be 3. So we're going to pick the lowest number. Okay, so if you put this together, it becomes 2-ethoxy butane. Okay, butane is a 4-carbon piece, right? So with that, and we have an ethoxy piece hanging off of carbon 2. So there you go. Okay, so with that, okay, so we're also going to have one where we take a name and do the drawing. When you do that, the easiest thing to do is to start backwards. Okay, so just work your way backwards. So start with the main chain, right? So cyclopropane, right? So propane is 3 carbons long, but it's a cyclo, right? Which means it comes back onto itself, which means that it is a triangle. Okay. Now the nice thing about cyclos is you can put one wherever you want, right? So with that, so let's say it's 1, 2, 3 like that. Okay, so that means you have an ethyl, right? You have a 2-carbon piece hanging off of the propane. At carbon 1, at carbon 2, you have a methyl group. And notice how, right, the main chain is here, so this ethyl group is extending away from that chain, right? So it's a 2-carbon piece away from the main chain. Okay, so there we go. There's your structure. Not too bad. So start here, and then work your way that way. Okay, work backwards. It's the easiest way to do it. Okay, so functional groups. Okay. Now, so for that, I'm going to give you the molecule. Now you can ignore this. So I'm actually going to make the molecule. So for that, so to avoid some confusion, stuff like that. But I did want to show you some actual drugs here. So with that, so this is Symbicort. So with that, so this is used for asthma. So with that, and this 3 6-membered rings and a 5-membered ring here. So these guys here, that's an actual generic. That's a steroid structure. Okay, so with that, so then steroids just have different fruit hanging off of here, different functional groups. Okay, so it's your job is to identify them. Okay, so here we go. So we have, so you just start one end and work your way to the other. Okay, so here, right, so we have a C double bond O. Okay, definitely what you're going to want to do for these things is to look on both sides. So you have a carbon on one side and a carbon on the other. So that makes this a ketone. Okay, now here you have a double bond. Now it's part of a 6-membered ring, right? But you don't have that double single for the of the benzene, right? So this is just an aryl group there and there, or not aryl. This is a alkene. It's not an aryl. Sorry. So these are both alkenes. Okay, they're just C double bonded. They're not. I know they're part of a 6-membered ring, but you don't have that alternating double single. So that's when you have an aryl. They're just straight alkenes. Now these wedges and dashes, all those mean is that like the wedge is actually coming out at you, and a dash means it's going behind the paper. But we'll talk about that later. Stuff like that. So this is just a methyl group hydrogen here, right? Right there, you have an OH, an oxygen with an H on one side and a carbon on the other. Okay, stuff like that. So the so this becomes an alcohol. Okay, so you come along here. These are both as H's, right? So with that, so here you have a C double bond O, but there's a carbon on this side and there's a carbon on this side. Okay, it's not a carboxylic acid, because with carboxylic acid you'd have to have an OH right there. So this is just a ketone. Okay, and there's an oxygen with a carbon on one side and an H on the other. So this is an alcohol. I know the OH is very near the C double bond O, but that carbon makes all the difference in the world. Okay, so with that, okay, so these are over here. Now this looks like, right? So carbon, right? So this looks like 2 ether groups, and in fact it is. Okay, but because these 2 ether groups are hanging off of the same carbon, okay, this becomes one big group called an acetal. It's one of those special cases, and we'll talk about that more in just a second. Stuff like that. But this one here, 2 ether groups that are hanging off of the same carbon, that's called an acetal. Okay, stuff like that. And so you kind of come along here, and there's no double bonds, because really what you're looking for is you're looking for non-carbons, as well as these sort of double and triple bonds. That's really what you want to look at, look for. Okay, so there we go. That's Symbicort. Now, if we want to look at something like Tobias, which is used for overactive bladder, okay, so these guys here, okay, these are your benzenes. So these are your aryls. I don't expect you. I'm not going to put them on there, but I'm not going to expect you to mark these. If you can't find benzene, then we have bigger issues, stuff like that. But by the end of this course, I should say. So the alkanes, the cycloalkanes, and the benzene groups, you don't have to mark. I marked them here just so you know them. So these are benzenes, right? But you wouldn't have to mark these on your test. Okay, but for here, right? So you just start at one end, right? So here you have a C double bond O. On one side you have just a regular carbon. Here it's an O carbon. Okay, so that makes this an ester. Okay, I know that this is part of a ring, but that doesn't matter. Okay, now for here you have an OH, with an oxygen with a hydrogen on here on one side and a carbon on the other. So that makes this an alcohol. Okay. Now you're coming down here, right? So here, right? So a nitrogen with a C double bond O, okay, that's an amide. If it does not have a C double bond O next to it, it's an amine. Okay. Now the other one you have to worry about would be that group there. That's a pretty special case. That's a nitrile. If it's a triple bond to a single C, that's a nitrile. But pretty much, you look at a nitrogen and it doesn't have a C double bond O in it, and it's not a nitrile, it's going to be an amine. So with that, so there we go. Those are the groups. Okay. Now this is one of those special cases with the oxygens. Okay. So here, right? So you have a carbon on this side and a carbon on this side, right? So and they don't have other ethers coming off of that. So this one here is an ether. Just a regular ether bond, okay? But here, notice how there's two ethers. Now you'll notice that if you write a couple of ethers, they're right next to each other. Alarm bells need to go off, because what ends up happening is, notice how they are sharing a carbon, okay? That makes these, instead, that big group, be an acetal. Okay, it's two ether molecules that share a similar carbon. Okay, share the same carbon. So if you're writing ether a couple of times, alarm bells really need to be going off. That might be an acetal. Okay, this one here, notice how there's an ether over here, but there's no ether on this side, there's no ether on this side, so it's just a regular ether. Now here, this is an ether, okay, because it's an oxygen with carbons on either side. However, this is another one of those special cases where if the oxygen is part of a triangle, notice the triangle here, okay, notice the triangle there. This only works with triangles. This is called an epoxide, okay? And because it's part of a triangle, it becomes incredibly reactive. So regular ethers like this are pretty unreactive. Acetals can be reactive. Epoxides are incredibly reactive, and that's why we give them their own special name and group, stuff like that. It has to do with their reactivity. But we'll talk about how you make these, and these are kind of fun, stuff like that. But this is a special case of the ether. Okay, a regular ether is just going to be off by its lonesome. Two ethers right next to each other are going to be an acetal, and an ether that's part of a triangle, that's going to be an epoxide. Okay, so keep working on these. For that, so good luck.